Hello, students of mathematical studies, and welcome to our next video on probability. We're going to do about three things here. We're going to talk about the marble problem, we're going to talk about other coin tosses, and then we're going to talk about a card game. And a lot of these are going to relate to the concept of a tree diagram. If you're not already armed with your notebook and a pencil, go ahead and pause and get one. And you're back. That's fantastic. So let's talk about the marble problem. Students did some interesting things. Someone did use the Lego suggestion. Someone had Skittles coming out of a bag. People that did it found a lot of different percentages. We had 55% chance of winning. A lot of people did 20 trials. That seemed to be the standard on that. And some got 55%, some got 45%, some had 40%, some had 50%. As it turns out, the marble problem is a coin toss. Now, that doesn't mean that you're actually tossing a coin, but what it does mean is the odds of winning the marble problem, theoretically, were 50%. And at least some students hit that 50%, got 10 wins and 10 losses out of their 20 trials, hit that right on the head. Now, here's a framework that'll make it possible to understand this 50% thing with this piece of paper. Alrighty, so go ahead and draw a little circle at the top, and in the circle you can put the 4 marbles. You could do this in colors if you like, or you could simply write B1, B2, B3, and R. This way we're keeping the different blue marbles separate by calling them blue marble 1, blue 2, blue 3, etc. So out of that initial bag, even though we are drawing 2 marbles, what we want to do is break this problem down into 2 parts. So we'll pretend that we drew 1 marble and then another, right? More on that later. But what will happen is your first marble could be either B1 or B2 or B3 or the R. But then off of each of those branches, we're drawing a second marble. The second marble then is coming from the remaining 3. So down the B1 branch, you'll have B2, B3, and R. The B2 branch will allow you a B1, a B3, and an R. The B3 branch allows you a B1, a B2, and an R. And the R branch will allow you a B1, a B2, and a B3. Those are all the outcomes. So how you read this thing is maybe you drew the red first, then B1, or maybe you drew B2 first and then B1. So all these different possible outcomes. When you look at this, you'll see the small branches on this. There are 12 of them. Of those 12, all 3 of them over here are winners because red first means that you can only draw a blue next, and those are mismatched marbles. Say that 5 times fast. And then you win. Over here, blue and only the red will have you win. Same for this one and this one. So there are 3 ways to win over here, 1 each, and 3 ways to win over here, all 3. 3 plus 3 is 6 out of the 12 outcomes. 6 out of 12 is 1/2. 50%, the marble game or the marble problem was a coin toss. Now, you may notice that this branch here of red, then B1, and this branch over here of B1 and then red were actually the same outcome, that you had B1 and red in your hand. And that's true. But that double counting we don't have to worry about because we've said these are, by saying, we'll call them marble 1 and marble 2, red then blue can be thought of as different than blue then red. Either way, it's a winner. And it is one of the possibilities is red then blue, and another possibility is blue then red, if we break it down that way. So 12 possible outcomes, 6 winners, that's a coin toss. Now you may recall that last semester, right before finals, we worked on the Skittles project. And in the Skittles project, we were looking to see how likely is it that a bag of Skittles has a certain number of candies and whatnot. We were actually analyzing the normal curve. But when we did that work, we also worked with the pennies. And we had a project where we were tossing 8 pennies at a time and counting how many of them came up heads, how many came up. Well, we didn't have to count how many came up tails. We had 8 pennies. If 5 of them were heads, 3 of them were tails because there were only 2 possibilities here. So when we set up a framework for that, and we're going to just build, we're not going to do the whole 8 penny thing, but we're going to analyze how we found these theoretical possibilities on that one, is that if you're tossing just 1 coin, your options are head and tail. But if you're tossing 2 coins, that option for the second coin still winds up being H or T. So we do HT and then HT. But for the other coin, it could be HH. Well, it could be heads or tails. What we'll do is we'll go HH and TT. For a third coin, we're not going to do 3 H's and 3 T's. Instead, we're going to take 2 to the 3rd power and say we have 8 possibilities. Half of them are going to be heads first, half of them are tails first. This is because with 3 coins and there being 2 sides of them, we have 2 things times 2 times 2, so 8 possibilities, similar to that 4 times 3 that was happening with the marble problem. So when tossing 3 coins, there are 8 possibilities. One of those 8 possibilities is all heads, one of them is all tails. And let's see now. You can build that whole table yourself. Well, actually, the table will show up right about on one of these two sides in a moment. There it is. And that's a table of 3 tosses. And from this, then you can start looking and saying, out of the 8, how likely is this, and how likely is this, and how likely is this. As that table grows and grows and grows and grows, and the number of tosses increases, if you graph it, what you do get is what looks closer and closer to a normal curve. And that's what a normal distribution actually is. So if I wanted to ask you, for example, to figure out the likelihood that you toss, actually, let's try this one. Suppose there's a game where the game is that you show up with 8 quarters and you drop the 8 quarters into a plexiglass container, like maybe let's say, yeah, whatever. It's got a thing on the bottom. Drop them all in there, and you look at them. If there were, let's say, 6 heads or more, you win $5. If there are 5, 4, 3, 2, 1, or 0 heads, then you lose. Now, how much does it cost to play this game? It cost 8 quarters, which is $2. So you gamble with $2, and if you get 6, 7, or 8 heads, you win. Would this be a game that would be worth playing, or would this be a game to avoid? That is a question to work up. Okay, so that'll be one part of the assignment. The other part will be an easier tree diagram to do. So we've got a quarter question, and we're going to have a card question. Now, when it comes to a deck of cards, take all the jokers out, you'll have 52 cards in there. 52 happens to be 13 times 4. The hearts and spades and clubs and diamonds, those are called suits. So there are 4 suits in a deck of cards. The ace, 2, 3, 4, etc. up to 10, then jack, queen, king, those card values are called ranks. There are 4 suits and 13 ranks, and 4 times 13 is 52. There are 52 cards in a deck. Here's the challenge for this one. Suppose there is a game where you shuffle a deck and you deal out 2 cards, and that's it. You deal out 2 cards, okay? If of those 2 cards, one of them is a face card and one of them is not a face card, then you win. If anything else is happening, 2 face cards or no face cards, you lose. How easy is it to win this game? Work that one up as an actual percentage. Now, in this case, you can't actually play that game over and over. You could play that game over and over again and find out. But I'm not going to say, hey, if you haven't got a deck of cards around, write one on a piece of paper, because making up a deck of cards would be a lot of work. So this one will be purely theoretical. What are the odds of winning this particular game? All right, you deal out 2 cards. If one of them is a face card, oh, quick thing on the face cards. They are the jack, the queen, and the king. So there are 12 face cards out of the 52 that are in a deck. All right. Now you might think the odds are just 12 out of 52, whatever that happens to be. Let's simplify that a little bit. Not going to simplify very easily. It's going to be 3 out of 13, and 3 out of 13 is an ugly number. But you know, you can push buttons and get a result. But that's not it, because there's a second card. So a tree diagram with probabilities will be a way to handle that one. I'm going to stop this video now, let you do that work, submit what you have, either as a picture or works. Oh, actually, this is just a percentage. We have the why would it be a good or a bad idea to play the pay $2 to play, win $5 if you win quarter game, where you toss 8 coins in and you've paid to play. And oh, by the way, on that one, you're not winning $5. You're winning $3 because you paid 2 to possibly win the 5. So you're either losing $2 or you're winning $3. You're not actually winning 5. Okay, so that's a way to analyze that one. So 6, 7, or 8 heads, and you win, and it costs $2 to play, and you win a $5 bill, getting a net gain of $3 in that. So work on that one and the other one. Is it worth playing that quarter game? And what are the odds of winning that card game? And the answers will be up tomorrow. Thank you.